All right, hi everybody, this is Mr. Shirlen. We're gonna go ahead and do the notes for Standard 17, Day 1. Let's take a look at the top of the page here. So we are looking at some examples of some things that are not polygons and some examples that are polygons. And what I want you guys to do is to pause the video and just take a minute to think about what the differences are between each set. So I'm gonna pause for a few seconds to allow you to pause the video, and then we'll talk about some of the characteristics that differ between these two sets. Okay, so hopefully some of the characteristics that you were able to come up with, when we look at the figures on the left that are polygons, those are all closed figures. Okay. They also all have, as opposed to say this one right here that's curved, none of these have that kind of characteristic, so these are all going to be straight edges. We also see, so on the figures that are not polygons, we see some lines crossing, and over here we don't see that. So maybe you wrote down that there are no intersecting lines. I'm not sure if you could tell this or not, but with this figure right here, this is actually a three-dimensional pyramid. Okay, so, and this is not a polygon. We can see over here that all of these figures are plane figures, or we call them 2D figures. Okay, so those are just some of the things that maybe you came up with when you were looking at those examples. So our definition that we're actually going to use for a polygon is going to include some of this in it. It's going to be a closed figure with at least 3 sides and we call those sides segments. So at least 3 sides or segments connected end to end. Okay. All right, so that's the basic definition for a polygon. And now what we're going to do is we're going to take a look at some different specific types of polygons. All right, so if you look at the next definition, that is pronounced equiangular or equiangular. So an equiangular polygon is going to have a focus, or we're going to be focused on the angles. And as we can see in this figure, all of these angles are equal to each other. And in fact, all of those angles are 90 degrees. And so when we talk about an equiangular polygon, we are talking about a polygon with all equal, or a term that we use a lot in geometry, all equal or congruent angles. So a polygon with all equal or congruent angles. Okay, the next definition we have is equilateral. So lateral is actually going to refer to the sides. And so if I take a look at the sides here, I see that there are tick marks on all 4 sides. And we know that in geometry, those tick marks actually refer to equal pieces, or pieces that are equal length. So equilateral polygon is going to be a polygon with all equal or congruent sides. Okay, so we talked about the angles of a polygon, we talked about the sides of a polygon, and now we're going to do a definition for a regular polygon. So a regular polygon is actually going to be, and this is an example of a regular polygon right here. A regular polygon is going to be a polygon that is both equiangular and equilateral. Okay, so we're talking about a polygon that has not only equal angles, and so we can kind of see these interior angles here. I know there's a lot of lines going on here. We're going to actually use this diagram here in a minute for some other definitions. But if we look at these interior angles here, this interior angle, this one, we can go all the way around the figure. Those are all equal. And we see the double tick marks on each side, which means all the sides are equal. So a regular polygon is going to be a polygon that is both equal angular and equilateral, all equal angles, all equal sides. As we're talking about this regular polygon, we're going to go ahead and do a definition for the center of a regular polygon. So the definition for this is going to be the point inside the polygon that is equidistant from each vertex. Okay, and we can see over here in our diagram that the center of our polygon is right here in the middle. And we also can see that the distances from each vertex to that center by these tick marks are all going to be an equal distance. Okay, so that's the center of a regular polygon. It's that point that's the same distance from each vertex. In order to create what we want to talk about in the next definition, which is a central angle of a regular polygon, in order to create that, this angle is formed by two lines from consecutive vertices to the center point. Okay, and so when we take a look at our diagram one more time here, consecutive vertices would be like if I wanted to connect this vertex to the center and this vertex to the center. What I have marked here is there's an angle formed by connecting those consecutive segments that go from a vertex to the center. So I have this central angle. Now this central angle, think about this for a second. If I go all the way around this center, how many degrees would that be? Well, around this center looks like it's a circle. And so how many degrees are in a circle? I know we've talked about this before, so many of you are probably thinking 360. So think about this. This central angle here is a piece of that 360. All of them together would be 360, and that's just going to be a piece. And we'll talk more about that later on. Okay, so that's a central angle. Let's continue down the page here. We're going to talk about something called symmetry. We're going to focus on what's called reflectional symmetry. Okay, the definition for reflectional symmetry is the line you can reflect or fold. The line you can reflect or fold over where both sides are equal. Okay, the line you can reflect or fold over where both sides are equal. So a figure has reflectional symmetry if you can fold it over onto itself so that both sides of that fold are completely exactly the same. That axis of symmetry is actually the line that you fold or reflect over. Okay, so figures can have no reflectional symmetry. They can have a single line of reflectional symmetry, or they can actually have multiple lines of reflectional symmetry. If you can determine that you're able to fold a figure a bunch of different ways, then you can figure out if it has more than one or exactly how many lines of symmetry it has. So what I'd like you guys to do is to take a minute and go ahead and look at 1, 2, and 3. and just kind of on your own right now, think about how many lines, if any, these figures, how many lines of reflectional symmetry these three figures will have. If you'd like to pause the video here, I'm going to stop for a few seconds. You can pause it, take a look at those, think about them, and then come back and we'll discuss it. Okay, let's take a look at number one. So problem number one here, because it looks like only these two sides are equal in length, this looks like it's shorter. Here is how you can show that it has reflectional symmetry. There's an axis of symmetry, or a line that can be drawn right down the middle right here. And then think about if you were to fold that top piece down onto that bottom piece. So your fold would be right here on this line. If you folded that down, they would completely, perfectly line up. So that figure only has one axis of symmetry. There's no other way I could draw a line that would be able, or that would allow me to fold it over onto itself for that one figure. For the second one, for this one, we definitely have a line of reflectional symmetry down the middle. You can kind of picture folding it over onto itself. And we have a horizontal line of reflectional symmetry. We can kind of do the same thing right here. It may kind of look like there's a line of reflectional symmetry that's diagonal here, but I want you to notice that how this line right here is longer than this line. So if I go to draw a line of reflectional symmetry here, and I try to fold this shorter side over onto the longest, it's not going to match up. So this one only has two lines. If we take a look at number three, we can kind of start off the same way we did number two. Okay, I can see how I can fold it this way, or I can fold it this way. This one does, because all of the side lengths of the figure appear to be equal, this one does have some extra lines of symmetry diagonally through the figure. So I have a total of 1, 2, 3, 4 lines of reflectional symmetry, or 4 axes of symmetry. So that's just an introduction to that topic, and we're going to take a look at some more of that, or incorporate that in the notes in the back of this sheet. So go ahead and flip your page over. Okay, we're going to take a look at 3 different triangles here. The directions say label each picture as equilateral, isosceles, or scalene. I don't know, if you guys all remember those definitions or not, but we did talk about equilateral. Equilateral is a triangle that has all equal sides. So for these 3 figures, it looks to me like this is going to be our equilateral. Okay. If you don't remember, isosceles refers to a triangle that has 2 equal sides. Okay, so if you look through the picture here, it appears that this first triangle here is going to be our isosceles. And then scalene actually refers to a figure or a triangle that has no equal sides. Okay, so we're going to do a little investigation with these 3 triangles here. We're going to take a look at, this one's scalene, okay. We're going to take a look at not only the angles of the figure, but we're going to determine how many lines or axes of symmetry they have too. So what I'd like you guys to do is go ahead and take your protractor, and I want you to go ahead and measure the interior angles on this triangle, the second triangle, and the third triangle. I want you to take your time with that. We're going to come back and have a discussion here. So pause your video if you need to, and then we will talk about what those angles are and be able to fill out the table together. All right, so hopefully you're able to take a look at the triangles, measure some of those angles. These are the measurements that I came up with on my own. So I got that this was about 70 degrees. This angle is about 70 degrees, and that this angle is about 40 degrees. In the second triangle here, I got 60 degrees for the bottom corner. I got that this one was pretty much 90, and that over here, this corner was 30 degrees. For the third triangle, when I measured those angles, for each angle I got approximately 60 degrees. So all 3 of those are the same. So kind of think about that for a second. In this equilateral triangle, so it says what type of triangle, this is equilateral. The number of congruent angles was 3. So there were 3 congruent sides, and we had 3 congruent angles. Okay? Let's talk about isosceles. For the isosceles triangle, we had 2 congruent angles. Well, think about that. Isosceles means we have 2 equal sides. So we had 2 equal side lengths, we had 2 equal angles. Now for the scalene, none of the angles were the same, so we had no equal angles. So no equal sides, no equal angles. Also think about where the tick marks are in these figures. In isosceles, these are my equal sides, and if you look across from those equal sides are equal angles. In this equilateral here, all 3 sides are equal, and all the angles across from those sides also have the same measure. So just kind of keep that in mind. That is definitely a good connection to make. Now let's talk about axis of symmetry. So where would we find an axis of symmetry for the equilateral? Well, it turns out for the equilateral that we can fold it across this line that I just drew vertically. We can also fold it across this line, and then there is a third line right here. So from each vertice to the opposite or through the opposite side, there's going to be a line of symmetry. We can fold it here. We can fold it like that. We can fold it, I missed one of them. Oh, we can fold it up like this. Okay, so for our equilateral triangle, we have 3 axes of symmetry. There are 3 different ways we can fold it over onto itself. Now look at the isosceles. The only line of symmetry that we have for this isosceles triangle is going to be right down the middle. That's the only way that we can draw a line where we can fold it over onto itself. And so that isosceles is going to have 1 axis of symmetry. Now for the scalene, if we try to draw an axis of symmetry or a line of symmetry, we're not going to be able to find anywhere that we could place it so that we could fold the figure onto itself. It's not going to match up just because of those 3 different angles and the 3 different side lengths. So we're going to have no axis of symmetry for that. Okay, so that's just kind of a crash course in the relationship between the number of equal sides, number of equal angles, as well as some more practice with the axis of symmetry. We're going to move on to the last concept for the notes for today, which is rotational symmetry. Okay, so reflectional symmetry had to do with folding over onto itself. Rotational symmetry, the definition is going to be when the object is spun, okay, so we're talking about turning it, and we're going to be specific here. Oops, hold on a second. So when the object is spun, and what I mean by that is, rotated or turned, but specifically less than 360 degrees, and looks the same. Okay, so we're talking about if we take a figure and we turn it, if we rotate it, if we turn it around, and before you get all the way back around, you see the same figure repeat itself. Okay, so think of some things that have some symmetry. We could take a look at this. Now imagine that there's not a line here, that there's no lid, that it's just one solid shape. As I start to turn this or spin it, before I get all the way back around, I see a repeat of the original shape. Okay, so that would be rotational symmetry. If I keep going, I don't see it again until I get all the way back around. So that doesn't count. If you have to go all the way around 360 degrees to see the same shape again, that's not rotational symmetry. That's just turning the figure all the way around. Okay, but if you have a figure where, let's say in this case, I rotated it 180 degrees, and I see the same shape again. Okay, so we're gonna take a look at some figures down below and do an investigation having to do with central angles of these figures. And I do want you to kind of think about, You know, do you think these guys have rotational symmetry? Do you think that you would see the same figure again if you were to turn it? And I think we can, you know, we could kind of just turn the page with the triangle and see, yeah, I could turn it and see the same figure again before I get all the way back around. And I think the same is also going to be true for the other figures here. Now, something to notice as we talk about these figures is that we are working with regular polygons. And that means that all the sides and angles for these figures are going to be equal. The job that I have for you guys to do is that we're going to figure out the measure of a central angle for each one of these figures. Here's how you make the central angle and how you can kind of make it so that you'll be able to measure it. So to measure the central angle, first we've got to create it. Now remember, a central angle goes from, it's going to be 2 consecutive vertices, and we're going to draw segments from the center through those vertices. So if I make this a little bit longer, it's actually going to be easier to measure with my protractor. So I'm going to go past the vertex, okay? And then I'm going to do the same thing down here. And that's going to make it a little bit easier for you guys on your protractors to figure out what these measurements are. And so we're going to actually do this for all 5 figures. So I'm going to draw my angles first, and then I'm going to go back and we'll take some time to measure them. All right, so for this second one, this square here, we're going to do the same thing. We're going to connect the center to 2 consecutive vertices. Okay, just making it longer because it's going to be easier to measure like that. For the third one here, this pentagon. Okay, for this hexagon. And finally for this heptagon, 7-sided figure. All right, so we have all the central angles drawn. Now, what I'm going to do is I'm going to give you guys a chance here to take your protractor and go ahead and find the measurements for these angles, and we're going to see if we can look for a pattern here. All right, so I'm going to stop for just a second. You can pause the video if you'd like and go ahead and measure those angles. Okay, so let's talk about those measurements that you hopefully got for these angles. If you measure this central angle right here, you should have gotten a measurement of about 120 degrees. For the second one here, this central angle was actually a 90-degree angle. For this one right here, for my hexagon, this was 72 degrees. Sorry, that was my pentagon. For my hexagon, this is going to be 60 degrees. And then for my 7-sided figure, this ended up being, so we'll talk about this in a second, but it's somewhere between 51 and 52 degrees. Okay, so I'm just going to put 51 degrees for right now. Let's take a look at these for a second. So think about how many degrees did we say it would be all the way around? Well, all the way around would be 360. Well, in this figure, if I were to draw all of the central angles, there would be 1, 2, 3 of them. Well, think about what's 120 times 3. Well, it's 360. So there were 3 of them, and each of them, maybe we could assume each of them would be 120, and 3 times 120 would be 360. Well, if we look in the second figure, the second figure would have 4 central angles. Think about what's 4 times 90. It's also 360. So we're kind of seeing a pattern develop here where we could actually figure out or calculate the central angle without having to keep measuring these in the future. So this is going to be a formula for our central angle. To calculate your central angle, if you think about it, you're always starting off with 360. Okay? And in this one, what's 360 divided by 3? And remember, that's the number of sides. 360 divided by 3 is 120. 360 divided by 4 is 90. Check and see what 360 divided by 5 would be. I bet it's going to be 72. So if I divide If I divide 360 by the number of sides, that's going to give me my central angle. And when you do this for the 7-sided figure, you actually get something like 51.42 degrees. Okay, so if you ever want to find the central angle of a regular polygon and you know how many sides it has, you can do 360 divided by that number of sides, and that's going to tell you that value. So these were the standard 17 day 1 notes, and there's also a second video this week for standard 17 day 2.